Hey guys, these are going to be the first part of our 6.4a notes. All what this lesson is about today is representing functions with integrals, and then when we get back on Friday, we're going to talk about the fundamental theorem of calculus. And so it's essential that you understand this part before we get into the fundamental theorem of calculus. But this first page is just a review. So we have a couple problems. This first one is the integral from 0 to 1 of f of x dx. And so just a reminder, what the integral means is it's the exact area under the curve, so whatever function was stated, from the bounds. So in this case, we are trying to figure out the exact area under the curve or between the curve from 0 to 1. So these are the this is the section right here I'm looking for. I'm just trying to find the area under the curve, and I know that this technically isn't under the curve. So another way, we normally use under the curve as the language, but a more specific way, more exact, is between the curve and the x-axis, or the function on the x-axis, because technically this graph of f that you see in this picture isn't a curve, it's just a function, it's a linear function. So we're going to start by finding the area here. And so the area of this section right here, I can just use the triangle formula because it's a triangle. So that's 1/2 base times height. So I'm going to start with the 1/2. The base is 1. And the height of this is 2. And so if I multiply that all together, I will get 1. Now the thing is, if it's ever below the x-axis, it needs to be negative. So the answer to this one is going to be a -1. And that is because it's below the x-axis. So this space right here is -1. This next section wants me to find the area from 0 to 3. So I already have the area between 0 and 1, so I'm just going to put plus there. But now I need to add on this area right here from 1 to 3. And again, this is just a triangle formula. It's going to be positive area because it's above the x-axis, and this time the base is 2 because this section right here is 2. And then this is the height right here. So this is the height because it's the part that makes a right angle with the base. It's the line that makes a right angle with the base, and the height is 2. And then I need to divide everything by 2 as well because it's 1/2 base times height. That gives me, oh sorry, this over here should have been a -1. So notice I just changed that to a -1. So I'll have -1 plus 2, and that gives me 1. So that is the exact area under the curve between 0 and 3. That is the integral between 0 and 3. And then I'll do it one more time between 1 and 3. I actually just did all of that work in the last problem though. 2 times 2 divided by 2 is 1. So that is the area specifically between 0 and, or between 1 and 3 right here. So that is just kind of a review of how integral notation works, and that is what it means. And so an interesting thing you can do is you can define functions using integral. And so for example, we have this integral right here. And it's the integral from 0 to x, which that looks a little funky right away, but we have the integral from 0 to x of 2t dt. And we are calling that integral g of x. Now I know that you see t's here, but the reason that this integral is called g of x is because it is still, this function is going to be dependent on what x is. And so that's why this function over here, that's why it's a g of x, not g of t. And so I wrote down here, how do these integrals look different than the ones we looked at last week? So go ahead and pause that and try to think for a second, pause this video, and think, how do these integrals that I'm looking at right now look different from what we did like this week / like even on this page right here? The number one thing I see is that the bounds are different. The top bound is a variable. It's an x instead of a value. So if you look here, we have the bottom value of the bottom bound is still a 0. The bottom bound here is still a -2, but the top one is x. And if I go back to this page up here, the top bound was 1, the top bound was 3, the top bound was 3. And so there was always a value in there. And so the reason this notation is important is, let's say we have a new curve. I'm going to call it k of x. I'm going to call this integral 1 to 3 of f of t dt. So I'm going to call this function k of x altogether, but it is defined by the integral of f of t from 1 to 3. And so what this is right now is k of x is going to be the area from 1 to 3 of f of t. So it's the area under the curve from 1 to 3. But say I didn't want to go all the way to 3. What if I wanted to find the area from 1 to 2? So I'll change this to a 2. And then I would do a line here instead at 2. And I would just be concerned about this area instead. So I could always change that top bound. But what if I just didn't know what I wanted my upper bound to be? I wanted to start at 1, but I didn't know how far I could go. Well, then what you would do is you would just pick a number between this and you would just call it x. And so that would represent the area between 1 and some unknown bound. And so that's where this x comes from. It's saying we're going to start finding the area under this curve at this point, but we don't know what our final is going to be. And so we're going to put an x there to represent this unknown amount of space. And so that's where this notation comes from. And so going on to the next page, I'm going to show you an example of how this works. So, sorry, the table looks like pretty messy, but I have a function g of x equals 0 to x. Sorry, I'll say it again. G of x equals the integral from 0 to x of 2t dt. It is a function defined by an integral, and we're going to fill in the table using that integral. So this is going to look a little funky at first, but what we're going to do here is I'm going to redraw this table so it's like a little bit more organized. We'll use this instead. Okay, so for g of 0, we know that we want x to be 0. So g of 0, what that's going to do is I'm going to plug in 0 for x, and then anywhere in the integral I saw an x, I'm going to put a 0. And so this is kind of how we set it up, but what does that actually equal? So to figure that out, we're going to have to look at the graph of 2t. So I'm going to sketch a graph over here. And my graph, I'm going to make my x's go to 3, because if you look at the x values on the left, they only go up to 3. And then I'm going to count by ones, and I'm going to go all the way up to 10, and you'll see why in a second. 2, 9, 10. And I'm going to graph on this plane over here. I'm going to graph 2t, aka y equals 2x if you were to change the variables. But I'm going to graph 2t. So that's just a linear function with a y-intercept of 0. So I'll start at 0. And then the slope is 2. So I'm going to go up 1 over 2, up 1 over 2, up 1 over 2. And so this is what my line is going to look like. It's just a line. And so what this integral over here is telling me is it wants to find the area under this curve from 0 to 0. Well, 0 to 0 isn't an interval, and so you can't actually find that area because it doesn't exist. You can't find the area from 0 to 0. So that doesn't even exist, so the answer to this one is 0. Let's try g of 1 now. So I'm going to replace the x with a 1, and I'll do 2t dt. So now this is going to make a little bit more sense. This is asking me to find the area under the curve 2t from 0 to 1. So just this section right here. And it's just a triangle, so I just need to use the triangle formula. It would be 1/2 base times height. The base is 1, and the height is 2. And so my answer to this is going to be 1. Because 1/2 times 1 times 2 is 1. And so that means g of 1 is 1. Try it if you want to. Go ahead and try the next two. You are welcome to pause, but I'm going to keep going. So g of 2 wants us to find the area under this line from 0 to 2. And so it's still 1/2 because it's still a triangle. The base is 2 and the height is 4. And so I will get 4 as my answer. And I'm just going to do the next one. I'm not going to talk about it. So that tells me that g of 3 is 9. And so that is how you actually use a function that's defined by an integral. So we're going to do one more example on the next page, and then we're going to kind of do some more word problem-based problems with this. So example 2 says h of x equals the integral from -2 to x of f of t is a function defined by an integral. Find h of 1 and h of 2. So feel free to try this on your own and pause this, but if I'm trying to find h of 1, I'm going to take this integral, and anywhere I see a 1, I'm going to x, I'm going to replace it with 1. And so what this is telling me now is that h of 1 is the integral from -2 to 1. So it's the area under the curve from -2 to +1. So that's this area right here. And as I look at this, I see that there are two shapes. I see a shape that's a rectangle, and then I see a shape that's a triangle. And both of those shapes, I am capable of finding the area. So I'm going to start with the rectangle. Its base is 3, and its height is 5. So that means this technically is just going to be 15. And then I have this triangle with a base of 2 and a height of 1, and then it's 1/2 base times height, so I have to divide that by 2. And so what I'm going to get out of this is 15 plus 1, which equals 16. So this is, that triangle right there is 1, its area is 1. And so altogether, the area of that is 16. Okay, now I'm going to do the last one. You're welcome to try it on your own. So -2 to 2 of f of t dt. So the thing is here, I already know what the area is from -2 to 2, so I'm just going to write down 16. And so I'm really just only adding in this next sliver. Or sorry, I already knew that part. I'm going to go all the way to 2, so I'm adding in this next chunk. So I know the area already from -2 to 1, so I figured out all of this area in the last part. I just need to add this last sliver over here, and so that is just another rectangle with a base of 1 and a height of 5. So then this h of 2 is going to equal 21. So using my integral, I figured out that h of 1 equals 16 and h of 2 equals 21. Okay, we're going to go on to our practice problem, and you're welcome to try this all by yourself. I feel like if you really put your mind to it, you might be able to do it without following along, but if you would like to follow along, that's okay. So this practice says you have taken over as a manager of a struggling umbrella company. Umbrellas are manufactured at a rate given by g of t equals 20t minus t squared. Umbrellas per hour for 0, which is less than or equal to t, which is less than or equal to 14. And t represents the hour after the factory opened to the morning 6 a.m. G of t is graphed below. So g of t is graphed right here. And this is the rate of umbrellas being produced. And so just a reminder, we did this on the first day of this unit, but since we have the rate of the umbrellas being manufactured, the area under the curve, under the rate function, what that will give you is the total accumulation of something. So if you took the area under the curve of the rate of change of rain one day, if you took that area, you would figure out how much it actually rained that day. And so if we take the area under this curve, we would figure out the total accumulation, specifically in this situation of umbrellas. Because this curve is the rate of umbrellas being produced, the area under it is the amount of umbrellas being created. And so this says, after, and we're going to need that to do this problem, after a leisurely breakfast, you arrive at 9 a.m. Write an expression that gives you the number of umbrellas that have been produced before you even arrived. So that means I want to find the area under the curve from, they started making umbrellas at 6 a.m., which is just going to be 0 because it says T represents the hours after the factory opens in the morning. So T represents hours after the factory opens up in the morning. So 0 would represent 6 a.m. So then 3 would represent 9 a.m. So we want to find the area under the curve from 0 to 9. or sorry, from 0 to 3, because that would tell us the amount of umbrellas that were accumulated from 6 a.m. to 9 a.m. And area under the curve, an exact area under the curve, is represented by a integral. And so I'm going to put 0 here because that's the time they started making umbrellas, and then to 3 because that's what's equivalent to 9 a.m. So those are our bounds. And then I'm going to put g of t dt. And it just wants me to set up this equation here. It didn't ask me to find it. It just wants me to write an expression. So this is our expression right here. That represents the area under the curve from 0 to 3. Okay, now it says roughly how many umbrellas were used. So roughly indicates to me that I can use an approximation. And so I am going to approximate now the area under this curve. And the reason I'm approximating this time is because this shape right here is not a shape that I know how to find the area of, because that is not a straight line, that is a slanted line, that's a curved line. And so I don't know how to find the exact area of this, but I'll just approximate. And it doesn't tell us how to approximate, so we don't necessarily have to use a left or a right Riemann sum. We don't have to use a midpoint or a trapezoidal. What I'm going to use is this almost looks exactly like a triangle. And so I'm just going to, the way I'm going to estimate this is I'm just going to find the area of that triangle because it really looks so close to a triangle. And so I see that my base is 3 of this triangle and my height is whatever this is. And I don't actually know exactly what that is. I know that the x value is 3 and then the output is represented by plugging 3 into the function. And so I'm going to plug that into this function right here because that would tell me what the exact area is. So I'm going to write this out real quick. Sorry, the bell is ringing. Okay, I'm going to finish writing this out and then I'm going to pause it and come back. So there might be kind of a weird gap here, but I have to do something during this period. So I'm just plugging 3 into that g function now. Minus 3 squared. I'll work this out real quick and I'll get 3 times 60 minus 9 all over 2. And if you put that in your calculator, I'll get 76.5. And so roughly the amount of umbrellas, I'm going to round. Since it says roughly, I can round. I'm going to put 77 umbrellas, was roughly how many umbrellas were produced from 0 to 3. And I will finish the next problem in a cut. So good luck. Okay, finishing off the video, the next question is really similar. It says at 12:30 you break for lunch, write an expression that gives the number of umbrellas that have been produced that day until your lunch break. So it's almost the exact same as last time. It starts at 0. And then 12:30 is 6.5 hours after 6 a.m. Then we're still working with g of t, d of t. So this is the expression that represents the exact area. And then now we're actually going to find that. So I'm going to go from 0 to 6.5, which is probably around here. And then to note, I already know what around this area is. This is about 76.5 because I found that in the last problem. And so when I go to find this problem,
please pardon this interruption.
Ignore that.
Amani Vai, please come down to the front office. Amani Vai, please come down to the front office. Thank you.
Okay, so again, it says roughly, so I can approximate. So I know that this section from 0 to 3 that we found in the last problem was 76.5. So I now only have to find this. And it doesn't specify how it wants me to approximate, so I can use any method I want. And this looks like a trapezoid to me. So it's pretty accurate, like just that. And it's one rectangle. There's only that tiny little gap of space that's being left out. And so I'm just going to find the area of that trapezoid. So the trapezoid area is base 1 times base 2. So this is going to be like g of 3. That's what would represent that height. And this would be g of 6.5. So I'm going to write, I'll like actually plug these into my equation in a second. I don't know what that's doing there. Okay, I'm going to divide that by 2, and then my height is just the area from 3 to 6.5. So that's 3.5. And then I would just plug that into my g of t function that I found. The g of t function is, sorry, I forgot what it was. Oh, it was right there. 20t minus t squared. So I would just plug in those values. So 76.5 plus, in g of 3, I figured out last time that was 51 in the last problem. So that's 51 plus, I kind of running out of space, but 20 times 6.5 minus 6.5 squared. And then I will divide all of that by 2 and multiply by 3.5. And I'm just going to go ahead and put that in my calculator. But I did it earlier, so I already know what it is. So it should be about 319. So the answer to that is the amount of umbrellas that were produced once you plug that in would be about 319 umbrellas. So again, just an estimate. But the last question here, I'll pause that for you guys to think about that for just a second or do these calculations. So finally, this last question says, write an integral. Write an equation involving an integral for a function f of x that gives the number of umbrellas produced x hours after the factory opened. So how does this connect to today's lesson? Well, it wants me to write an equation involving an integral. So I'm going to write f of x, and then I need to write my integral. And so we have figured out that 0 to whatever amount of hours of g of t dt, like that's what we've been doing this whole time. We've been finding the area under the curve g of t from 0 to some unknown. And so this is what the equation would be, because f of x is what f of x is going to stand for altogether is how much was accumulated. X right here stands for the hours after 6 a.m. because that's when they started working that day. And so it's like the amount of hours basically. And then this g of t right here is our rate equation. So we found that the integral from 0 to some unknown amount of hours of g of t equals how much was accumulated altogether. So that is the function we should get altogether. And specifically, we could even write it like this because we actually know what the g of t function is. We know that that function is expressed by 20t minus t squared dt. So that's just kind of like a practical example of how this connects to what we are learning. On Friday, we will finish the fundamental theorem of calculus, but these are just some things that we need to keep in mind to really understand the fundamental theorem of calculus. So I'm going to stop this video. Let me